Hello everyone. I am back. I am back with my Silver Jubilee webinar number 25. I always say the journey of 1,000 miles starts with a single step, and we took that step at IP on 5th November 2020 with the blessings of Almighty, my parents, wishes of my family, sports of my mentors and friends. From the bottom of my heart, we are thankful to one and all. And because of the good wishes and support, we managed to get through the tough time we faced. Thanks everyone for your support and blessings. These are results of extra efforts, passion, and commitment of my team at IPE. This journey of 25 webinars talks about the hard work behind the scenes and deserves a celebration. And to celebrate this special occasion, I have invited respected Baldev Narang Sir to talk on power equality. I shall be failing in my duty if I don't mention the names, force working behind this IP. Allow me to start with that one. First of all, I would like to thank Almighty, my family, my parents, my wife, my son. My mentors include respected PP Bhai Sahab, Anjali Chandra ma'am, KK Murthy Sahab, KK Gupta ji, NK Mittal ji, P Ramachandran sir, S. Abao sir, Hitesh Chauhan ji, and Dr. Kamal Bansal sir. My friends include Saket Gupta ji, Arvind Tukral ji, Dinesh Singh ji, Dr. Vikas Almadi, S.K. Batra ji, Vishandat ji. Last but not the least, the team working day and night, 24/7 for making this to happen includes Gulab and Ram Dhani. Respected participant, we usually talk about pollution, air pollution, water pollution, etc. But what about the electricity pollution we are facing these days? I mean to say, impure power, because these are not meeting the standards we have. In simple way, this is the power quality issues. In fact, there are three important parameters play a vital role, that is the voltage, current, and frequency. And the root cause of all these issues are reactive power, drawn, and the harmonics. To understand these two important aspects, I am with very special guest on very special occasion, subject matter expert, respected Honorable Baldev Raj Sir. Before I invite him to start his invaluable presentation on the very important subject, understanding of power quality, here comes a brief introduction about this legend. He is the CEO of Clariant Power System Limited in association with Fraco Germany. He is engaged in providing solutions in the field of reactive power and power quality to Indian and overseas customers in diverse field. He completed his BSc Engineering Electrical from Delhi College of Engineering, and when we talk about the experience he has experience of more than 45 years in large public sector and private organizations. He has good experience of international exposure of working with large EPC contractors, consultants, clients, and manufacturers. He has published several technical articles, technical presentation to industries, professionals, students, faculty, and he's running a blog by the name Power Play on Power Quality. It is worth to mention here that he is the chairman of capacity and the power quality divisions of IMA, engaged in working towards betterment of power quality practices and standards in the country. It also strives to ensure that good practices followed by one state are also adopted by other states. He is member of ETD01 of BIS, which is responsible for formulating power quality standards in India. He is also a member of Working Group 11 of ICTC08 on power quality, which prepares and recommends guidelines for IC quality norms. Now, without wasting further time, I would like to invite respected Baldev Narang Sir to please start your presentation, and we are very excited to listen to you on that very important subject of power quality. Over to you, sir. Share your screen.
Thank you, Rajeshji, for your kind words. In fact, today it will not be a presentation from my side. It will be a discussion, basically, an interactive session. And I'll very hurriedly rush through the slides so that we can give more time to our discussion and queries, whatever we have. And we'll go by that. And I thank all the people who have joined. We have a very special guest from Central Electricity Authority. And we have from some RE people who are developers of solar and wind energy plants. And we have a general gathering from various industries also. And some people from education field also are there. So let me straight away go to the screen, and I'll first rush through some slides of reactive power before we take the subject. And today, basically, I thought we will discuss more about issues concerning the integration of RE plants to the grid. And that has become a issue, and the industry is concerned, and CA also is trying to sort of improve the system. The failures are there, the problems are there, how we have to address all those things. We'll just try to find out the solutions for that also. So let me share the screen first. I hope the screen is visible.
Yes, sir. Please continue.
Okay. But why it has gone tilted? The screen has got tilted. I don't know.
So just right click and make it rotate.
Okay, I'll just try to find out because
Right.
it is there. Yes, it is there.
Yes,
Okay. Yes. Thank you.
It's okay. It's okay right now.
Okay.
Please continue.
So this is just I am from a company called Clarion Power System Limited. I'm a CEO of the company, and then we have association with Fraco Germany since our inception in 1998, and we have recently acquired one of the oldest capacitor manufacturing unit, Madhav Capacitors, Pune. And so let me go to this thing about the reactive power and the power factor correction. Suppose we have a load of 80 kilowatt and we have power factor of 0.8. So what we are doing is we are importing 60 kVAr of reactive power along with 80 kilowatt of active power. This is what is the situation. And then suppose we have no local system for power factor improvement like capacitors, we have to get this power from the reactive power from the grid only. So these days there are tariff structures which promote putting reactive power support in the industry itself, at the load itself. And the billing is designed in such a way that if you maintain power factor close to unity, you get all the tariff advantage. The billing has now gone to kVAH. So if you maintain unity power factor, all through your kVH and kWh are same, although it never happens in practical cases. But always people are trying to do that thing. And so that the dependence of reactive power being imported from grid is reduced. So this is what another picture. Active power and reactive power are the two items required for running any inductive, you can say, equipment like a motor. And the vector sum of this is apparent power. And I'll just take an example. Suppose we have a inductive load where the power factor is 0.7. And here what we will need is we will need to have 100 kilowatt is the load. So 100 kilowatt active power we are importing. And because the multiplying factor here is unity only, so reactive power also is 100 kVAr. So we are importing 100 kVAr of reactive power, 100 kilowatt of active power from the grid. And we need the demand sanction of 142 kVA to manage this type of arrangement. And then suppose we put the power factor improvement capacitor. Suppose we improve the power factor to 0.95. We need to put 67 kVAr. Still, we are importing another 33 kVAr from the grid. So what is done is, suppose we have here unity power factor, we will not be importing anything from the grid. And this is what the practice is today. Almost negligible power is being imported from the grid by industry. So this is a displacement power factor. We have later on slides on the harmonics where the displacement power factor is the basic power factor. And there is a true power factor which is inclusive of the harmonic impact on the system. So that is called distortion power factor, which depends on the THD value. So this is multiplied by the displacement power factor and we get the true power factor. And in fact, the harmonics also have their own reactive power requirement. They are also like normal 50 hertz supply system. They are also running into the system. They are also consuming reactive power, as well as some losses are there. And that is, we could call active power also is required by them. So this is affecting the overall reactive power requirements also. So these are just the multiplying factors we have for achieving unity power factor or whatever power factor we want finally from initial level. And we have the multiplying factors. We can just use this table to find out what is the KVR requirement. So this is how, suppose we have an initial power factor of this thing, 5.1, and we want to go to a power factor of 5.2. Our initial requirement of reactive power is this one, full requirement is there. Q 5.1, you can say this vertical side fully, and then the improved requirement is less. We have the difference of these two. And this is how we calculate this multiplying factor also from this table or from this diagram. And we don't always have to use this formula. We can just go to the chart, which is already made for all these conditions, and we can find out the requirements. So what is happening is the average power factor was earlier the criteria for giving incentives on the power factor. And that was for the entire month, the average was calculated. And now what has happened is the billing has gone to kVAH. So the power factor is not directly sort of required to calculate the incentives available. So kVAH has got built-in incentives for the power factor. So, and earlier there was a very big issue. People were using capacitors indiscriminately. They were using capacitors without any requirement just to get the full incentive. And everybody used to get full incentive, like 7% incentive was available in Maharashtra. And the requirement, even if they need, say, 1000 kVR, they were using maybe another 500 or 1000 even, or any amount without knowing what they were doing. They did not want to lose the incentive. So later on, this became a problem and unnecessary reactive power was being exported to grid, capacitive power. And that creates problem under low load conditions. And the over voltage problems were there. So, and this, to correct that situation, what the tariff structure was done, they made the deviation in the structure saying that the leading power factor also will be taken into account while calculating your kVAH. So when the leading power factor is taken, they continuously record RKVH lag and RKVH lead. And they use this formula to find out the actual kVH requirement. So when you are going to leading, so you don't get the full advantage. We had some cases where people came to us saying that our bills have shot up like anything. After this provision was made, people who are getting 7% incentive, they started getting maybe 15% penalty. One company we found that it was getting 35% penalty. Although they reduced the penalty to half, still it was so high. After introducing this kVH billing, the penalty was reduced as such, but still it was so high. And it was a result of using excessive power factor correction capacitors without any requirement. So now this harmonics have another, they have added another angle to the power factor also. So what is, there is a distortion. Instead of having a two-directional diagram, vector diagram, we have a three-dimensional. And a third dimension is a deviation due to harmonics. So if that is also taken into account, we have the kVH, the true kVH and the true power factor, everything changes. And this impact is there on the billing. If the tariff structure, so far, I don't think people have introduced, the electricity boards have not started using this distortion power factor for calculating the actual kVH. But maybe they will start sometime or the other if this becomes a problem. And then the people will have to see that the harmonics are also reduced. As it is, harmonics we have to take care in a different way as also because of the IEEE 519 guidelines, and there are penalties being imposed. So in any case, we have to take care of the harmonics. And the billing, whether it is there or not, still harmonics have to be taken care. And this is the impact. Suppose you have a power factor of 0.996 initially, and you have THD of 5%, your true power factor reduces from 999 to 995. And as the value of ITHD goes up, your difference between the true power factor and the other normal power factor is very high. Instead of 996 fundamental, the distortion, displacement power factor, 996 will become 925. There is a 0.07 increase, and that will increase your bill by 7% if it is taken into account. So I think before going to these other slides, what we'll do is we'll discuss, because today we have many people who are interested in the integration of solar or wind energy plants to the grid. So there are problems, there have been issues, because we have finished the reactive power part of the thing, and this is concerning the reactive power support only required along with induction of RE plants to the grid. So what happened in the past is recently, or maybe over a period of some few months or a year or so, there have been a lot of disruptions in plant capacities. That there were large-scale isolations of RE power, particularly in Rajasthan. The grid is very weak, and these plants got isolated because of the having no support for the reactive power available. The voltage could not be maintained, and they had to be sort of isolated. So this was the situation. So the agencies involved in integration, I think Grid India is one of the agency for that. So they made some studies and they recommended that to overcome this situation, repeated failures of the RE plants or grid interruptions, we have to have support, reactive power support by way of STATCOMs, means static solutions, instead of switched capacitors and switched shunt reactors. So this was based on some studies they had made, and the industry was not very much comfortable with this type of decision, because the plants were ready and they were waiting for being connected to the grid, and the permissions are not available. And these people have been asked to put STATCOMs, and STATCOMs at 33 kV are an issue basically in India. We don't have any capacity. There is no manufacturing capability available at 33 kV where we have to integrate these plants, RE plants. So that is one thing, whatever is required for this reactive power support, it has to be imported. Another thing is, the basic point was whether this is going to solve the problem or not. So we have been talking to CEA, and even the industry, the RE industry also has been talking to Grid India. They have been talking to CEA, and they are trying to understand why this STATCOM only is required and whether it is really going to solve the problem or not. So we also had a very marathon meeting with CEA from IMA also. I was one of the person who was leading that team from IMA. We are basically 4 major manufacturers, or so far I think the people who are only there to give the solutions, reactive power solutions to the this solar and wind plants. So all 4 of us had been there in the meeting, and we tried to put forward our points. And even industry, RE industry also has been talking, and they have been also trying to find out you can say way, whether it is really required or it can be, we can have some alternative to that. So I will just elaborate whatever points we thought are there regarding this integration, and where the STATCOM may not be a solution, because whatever it appears to be with the you can say things going on today, the mandatory requirement has been put, and it seems it has been thought of as a magical solution that it will solve all the problems. So what we found out, and we have given certain issues, we may not be fully correct, but we have put forward our points, and we are waiting for CA, we are waiting for Grid India to go back to the drawing board again and find out whether they are really able to solve the problem with this thing or not. So one thing is that they say that LVRT and HVRT situations are there, low voltage ride through and high voltage ride through. Whenever there is a issue in the system, whenever there is a fault condition, so then certain trippings occur, the load is going off or the generation is going off, and there is a requirement, sudden requirement of reactive power, either inductive or capacitive. So we have to have these conditions which have to be met instantly, immediately, within few milliseconds only, or could be close to a second or something, maybe. So these things are required. And STATCOM, if it is available, it will solve the problem. So what we have seen is, and we have tried to find out from the other overseas countries also what they have been doing and what was the situation there, what happened there. So what we came to know is that whenever there is a issue like that, whenever there is a fault condition, what happens is the STATCOMs, they go out of service within maybe quarter of a cycle, because their firing angle changes and they go out of service. So they are not available to support this reactive power requirement for which they have been they are being promoted. So that is one of the major reasons. So when they are not available, why to go for that? Even if we put, where is the solution going to come there if they are not available? And another thing is either it is STATCOM, or we can also have a similar solution by upgrading the capacity of the grid inverters, because grid inverters are same as STATCOMs only. They are handling active power normally now, but they can also handle reactive power. Their sizing has to be upgraded. Earlier in Australia, they used to have 140% capacity of the grid inverters, so that they can handle active and reactive power both. But now it is not being insisted upon, because they found that it was not necessary, and they have gone back to standard solutions. Whatever is available, whether it is switch capacitor bank or people want, they can go for STATCOMs also. I'll just admit somebody. Okay. Then whenever there is a fault, because this LVRT and HVRT is not a steady state condition, it comes only when there is a fault. And when there is a fault, another issue is that we have to feed the fault so that there is a speedy isolation of the faulty network. So these STATCOMs or even the grid inverters, they are not capable of feeding the fault. And there is a long delay in tripping the IDMT protections. So they are neither available to strengthen the grid fault conditions. They are not able to support the faulty isolation also of the system. And neither they are able to overcome the LVRT, HVRT situation, because they are not available during the situation when we need them. So we are still not able to understand why these things are being made mandatory when the real solutions are not going to come through these. So then we have to find out, suppose this is not going to work, then what is there to work? We know that if STATCOM is not working under dynamic conditions, under fault conditions, under LVRT, HVRT requirements, the capacitors, switch capacitors and switch shunt reactors also will not work, because if STATCOM will not work, they are also not going to work. So dynamic situation, nothing is working, whether it is a switch bank or it is a STATCOM or it is a grid inverter. So what is the solution then? So the solution is that we have to have a strong grid only. In a weak grid, the dynamic condition is going to create problems, such problems, and it will continue to remain. So we have to strengthen the grid. The grid strengthening, there are certain grid forming items, like we have synchronous condensers, which are able to sustain for a longer period. They can supply power, reactive power for a longer period during the fault condition, and they can see that the situation is overcome without any isolations and all. So that is one thing. Synchronous condenser is one of the solutions available, and it can also feed the fault also. Then we have a grid forming inverters as well. The normal inverters which we are having, they are just like STATCOMs only. They also will go out of service within maybe quarter of a cycle during a fault condition. So grid, what is this grid forming inverter is? It is backed by battery energy storage system, BESS. So it has a support available and it is able to ride through the situation. So these are the two solutions. So if we have to have a solution, we have to have a real solution. We cannot just say that STATCOM we put and we are through the problem. It is not likely to happen. So that has been our point of view. So even if we make the requirement mandatory, even if people start putting STATCOMs, the situation, whatever we have been facing, the isolations, whatever been happening, they will continue to happen. And the steady state condition, whether it is a switched bank, capacitor or shunt reactor, or it is a STATCOM, both work equally well. So there is no problem in that. So what is required is that we have to have some customization. So each location, we have to find out what is the grid strength, what is the actual requirement. And another thing is that we are making 35 or 33% as a mandatory KVR requirement. So what we have seen, we have studied almost all the solar plants or even many wind plants in the country, and we have found it is almost nowhere they require 33%. Some people need 5%, 10%, 15%, and all those things. So making 33% is also again as a blanket requirement is not workable. So it should be from case to case. Whatever is your actual requirement, let us go for that. And if requirement increases later on due to some changes in the grid structure, we can always upgrade those systems. So these are, and even in overseas, what we find, there are no such mandatory requirements. Component level, nobody goes to that level and says that you use this STATCOM or you use a switch capacitor bank. They simply say, this is the grid code. You study at this point where you are connecting. What is the requirement? You find out, you conduct the studies, you can run maybe ETAP programs or whatever you want and find out what is required, how much is required, and then go for the solution. So we are trying to have a blanket requirement as far as capacity is concerned, the KVR is concerned, as well as the type is concerned. So these are certain things which we found that all these things should be looked into before we make anything mandatory. And then earlier, the switched banks, capacitor banks or shunt reactors, they were not automated. All these things were only fixed banks only. And they could not, you can say, follow the load pattern and all those things. But today we have most of the installations today we are having, they are with 33 kV vacuum contactors. And these contactors can support within a second, they can switch on and switch off. So that is also available. There is a automatic requirement is maintained with that also. So with all these things in view, so that was our point, that whether we should have any mandatory requirements or whether we leave it to the case-to-case basis. And this mandatory thing has been done based on certain studies only on a weak grid. If the grid is strong, anything is workable, everything works. Because you don't need that, we can say, a situation where LVRT, HVRT, there are other systems available in the strong grid which can support that. So, and that is what most of the other places, things are working very fine, even overseas or even in India. In some places, we have seen this problem and we have made a blanket decision saying that let us go for STATCOM. So that was our point to CA to review the decision. So that is one thing. And I will just like, because I have been speaking on this point for a long time. So if I would like some people also to interact and let us have a some discussion on that. If somebody is having some opinion on that, let us try to discuss. Or if we want to have a discussion at the end, we can continue with this slides further, and then at the end we can have the discussion also. There is no problem.
Yes,
so
sir.
I was here.
Take question
Yes,
at the end also.
Yes, sir. Okay, sir. We will have at the end. Right, sir. So I had come up to this slide about the impact of harmonics on the system, the power factor and the reactive power requirement both. So there is another very important, you can say, aspect today. All over the world, people are using MPP capacitors for the low voltage installations. And there is a need of this because of the safety concerns. But in India, we still continue to use outdated APP capacitors. So that is one thing which I always try to emphasize in the discussions. The MPP capacitors are the latest development. They have self-protections, they have self-healing. Whenever there is a high inrush current due to any reason, the film evaporates, the metallization on the film evaporates, and the fault is cleared, and the system remains in service without isolation, it continues to work. Then there is an overpressure interrupter mechanism. Suppose these faults are very heavy in nature and there is a lot of gas formation, the overpressure disconnects the supply. The lid is lifted up and the physically connection, mechanically it is broken and the system is taken out of service. And then another feature is there, it is a segmented film today. Suppose there is a fault, it remains only in that segment and it doesn't travel throughout the film and doesn't fail the entire capacitor. So, and these self-protection, and then there is another one, contact ring we call, which is for the end connections. It makes this protection also work effectively. And there is no loss of MFD because there is no soldering involved in this thing. So these are the protections which are available in MPP and they are not available in APP capacitor. Another thing is when this capacitor fails, it is failing in an open circuit mode. It is totally isolating itself. It is not remaining in the circuit. And APP capacitor, on the contrary, it has no self-protection, and then when it fails in a short circuit mode, and it remains connected in the system as a thick wire. So what is happening is, today we have harmonics, or most of the loads are non-linear load. We are having harmonics and we are having resonance conditions. And during resonance, it is like a short circuit. And capacitor is an item which is taking the maximum burden of the this resonance condition, the short circuit condition. So this capacitor has to take the burden, and in case the resonance is there, very heavy resonance, it should isolate. It should work like a fuse. It should isolate itself so that the system is safe. The resonance is a self-correcting phenomenon. What happens is when this the capacitive and inductive reactances, they are equal, then this happens, the resonance condition. And if some capacitor blows off, this condition is broken and the resonance also goes away. So it is like a fuse. Otherwise, we don't have any resonance protection. There is no, you can say, relays available to save the situation from a resonance condition. But capacitor is an item which can save the situation and which can isolate, and the situation is normal again. But what we do is, whenever there is a failure of capacitor, we keep on replacing it till maybe there is an accident. It could be because of the resonance, but we keep on replacing. And the other thing is, if we have a APP capacitor, it never isolates. The resonance continues there most of the time, and the system goes into a very, you can say, problematic mode, and there could be an explosion or a fire or anything. So that is why this is one point which I always emphasize, the use of capacitors. Then power factor correction, we have these advantages. The KVA demand is reduced. The currents are less. We handle lesser current. Suppose we have a power factor of 0.9 or unity, there is a 10% current reduction in that. Similarly, the demand also reduces in the same proportion. The voltage profile improves when the capacitors are there. The voltage profile is more stable. The voltage is better. Then the system installed capacity is fully utilized. When we are running suppose most of the industry is running at unity power factor, the systems on the utility side, the distribution side, they are able to utilize their full capacity. And then all the penalties which are coming by way of poor power factor, they are removed if we have a good power factor. So now this was the end of the reactive power. Now we have the harmonics. So we have non-linear loads and we have harmonics and then again resonance conditions which we have to take care. So this is non-linear load means the voltage and current, they don't follow the same pattern. Voltage we are applying a sinusoidal voltage, but the current is not following the sinusoidal pattern. It is having a distorted pattern because of the non-linearity. We don't use the full cycle, full wave inside. So what are these non-linear loads? More than 70% loads today are non-linear, like UPS, DC drives, VFD, thyristor controlled heating, induction furnaces, arc furnaces, electronic chokes. All lighting, in fact, is non-linear today, whether it is CFL or LED or fluorescent lamps, everything is non-linear. Then battery charger, welding control, and rectifiers and SMPS supplies. So it is another slide which explains how the harmonics they are affecting the system and how we are solving it by passive as well as active means. So this is a transformer. We are representing the transformer and the system beyond that as a system reactors. And we are having a load connected in parallel to that. And this load is non-linear. So we are representing a current source, harmonic current source like this. And then we are having power factor improvement capacitors also connected in parallel. So these harmonic currents which are there because of the non-linear load, they flow through the capacitors and they flow through the system also, and they are getting exported to the grid, where they get converted into voltage disturbance, voltage harmonics, and they come back to everybody. And another problem is because this L and C being in parallel, they have a resonance condition at some point, and this resonance condition may occur at a harmonic frequency, and that harmonic will get amplified. So that is another problem. So what we do is we don't use plain capacitors. We use capacitors in series with a reactor, series reactor. So what it does is it does 2-3 jobs. One is that a reactor will dampen the inrush current. It will reduce that. Secondly, it will shift the resonance point to a safe place. Suppose the resonance was taking place at 7th frequency or a 5th frequency, it will come down and it will be there between 3rd and 4th, or maybe 2nd and 3rd, where there is no harmonic. So it is a safe place. So the resonance is avoided, the current is, inrush current is reduced. And third is that some harmonics are also absorbed by this. We are normally tuning this LNC circuit to 5th frequency, maybe close to 5th frequency, as say 189 to maybe 210 or 220 hertz, something. So this is offering, this LC circuit is offering a very low impedance to the harmonic current, 5th harmonic current. So that is absorbed by this thing, and thus it is not getting exported back to the grid. And in addition to the 5th harmonic, it also absorbs higher order harmonic to a lesser extent, maybe 7th, 11th, 13th, and all. So that is all the 3-4 functions we are able to achieve with the reactor in series with the capacitor. So if we are having only capacitor, it is going to cause resonance, and it is the export of the harmonics will continue. So now we have the norms and we have to maintain IEEE 519 norms. So this is a passive solution. By using the reactors, we can remove the harmonics. So harmonics, we have even number, 2nd, 4th, 6th, we have odd number, 3rd, 5th, 7th, and all. And this is one is a positive sequence harmonics and other is negative sequence harmonics. So because normally we get 5th and 7th harmonics because mostly our loads are 6 pulse converters, the non-linear loads. So we are having these harmonics mostly, and we have to take care of these harmonics mainly. And we have a third type of harmonics, which is multiple of 3, 3rd, 9, 15, 18, 21 and all. So these harmonics are called zero sequence harmonics. So they are normally available in single phase loads, where the concentration of single phase loads is higher. Like in IT installations, hotels, hospitals, commercial buildings, we will find this zero sequence, third harmonic mainly. So what is happening is these harmonics, they, along with the unbalance in the system, they flow through the neutral. and the neutral gets overloaded. So what we have to do is we have to strengthen the neutral. In IT installations, we find they use 5-core cable. They use 2 cables, 2 cores for the neutral and 3 cores for the phases. Because the neutral current could be more than twice the phase current also. And that is how it is, safety is there. There is no burning of the neutral. If we don't strengthen the neutral, there could be cases of fire, accidents, and all those things. And that is what we find in commercial buildings, hospitals, hotels. They don't use that double core. They don't strengthen the neutral. And they also have equally large number of harmonic currents. And they keep on flowing through the neutral. Neutral is very weak. The currents are very heavy, more than phase currents. And there are fires and everything. But this is not being taken care. And this continues to happen. So this is how a third harmonic is shown here. And here we have shown how the harmonic distortion is there. We have here third harmonic, fifth harmonic, fundamental current, and then the resultant current is shown in dotted line. So this is how the resultant current will look like. So we have this flow of harmonics. We have voltage harmonics and we have current harmonics. Normally, what we have is all the non-linear loads, they generate current harmonics and they flow from the load towards the bus upwards. From the load, they will go to the LV bus, then to MV bus, through the transformer to HV, and then back to the grid. And they get, every stage they get converted into voltage harmonic and voltage disturbance. And all this voltage distortion comes back from high voltage, from the grid to high voltage to medium voltage to LV. So this is the flow of harmonic. It happens like that. So when we are not able to control current harmonics, there is a big voltage distortion, big voltage harmonics in the grid, and that will affect everybody. And today the tariff structures are being made in such a way that consumers are responsible for maintaining current harmonics within limits. If they don't do it, they are penalized. And the voltage harmonics is the responsibility of the utility, the power supplier, to maintain voltage harmonics. If they don't maintain the voltage harmonics, because they will go back to every consumer, whether they have linear load or non-linear load. So they have to pay penalty to everybody for excessive voltage harmonics, which are out of limit of the IEEE 519 norms. So the number of people who will be getting the penalty from grids will be more than the people who are exporting current harmonics. So maybe these people are very slow in getting these norms implemented. So these are the adverse impacts of harmonics. There is an increased heating because of the iron and copper losses, and the performance characteristics of all the equipment, electrical, electronic changes because they are not designed for harmonic currents along with the fundamental. Everything is designed for 50 Hertz. But when all these currents are also flowing, the characteristics change. Then the neutral, as I explained earlier, the neutral overloading is there. Capacitor failures are the first indication of the presence of harmonics because capacitors act as sink for the harmonic currents. Their impedance to harmonic currents to higher frequency currents is very low, and all the harmonic currents find their way through the capacitors and the capacitor fails. Whenever we find excess failure of capacitor, that means the harmonics are there. Then there are spurious trippings of thermal protections. The bimetal overload relays or the releases, thermal releases, they maloperate because they are getting operated due to harmonic current. The fundamental current could be normal, still they operate. Then the controls also, there is erratic operation because they are also not designed for harmonic currents. Then communication interference is there. And sometimes even the meters don't read. The error measuring errors are there and the meters are not giving the correct values. So this is what I was explaining. If there is a resonance condition, the things can go to that worse condition. So these are the requirements. Normally, most of the people, the consumers are connected between up to 69 kV, and they have to maintain voltage harmonics are individual level is 3% and THD is 5%. And the current harmonic, mostly we have ISC by IL between 20 to 50. And we have to maintain TDD of 8%. Here we don't talk of THD because THD is not an indication of severity of the harmonics. We have to consider TDD. TDD is related to the maximum load current and THD is related to the fundamental current. And that doesn't indicate any, you can say, severity or at all. So we convert the whatever we measure THD from the analyzer, convert it to TDD. Now the meters themselves convert directly to TDD. And if the TDD is within 8%, mostly it is considered safe. So these are just formulae. Total harmonic distortion we calculate like this, and the THD is there, and then demand distortion is with respect to the load current, and THD is with respect to the fundamental current. So these are just simple formulae. And whenever we are connecting a reactor, as I showed earlier, in series with a capacitor for passive filtration, so the voltage across the capacitor rises. Suppose we connect a 7% reactor, means 7 kVR reactor for a 100 kVR capacitor, the voltage across capacitor will go up by 7%. So in case we have a 440 volt system and we are having 7% reactor which are normally used, the voltage will be around 473, and then we have to consider around some tolerance, voltage tolerance, about 10%. So normally we will be required to use 525 volt capacitors if we are using reactors along with the capacitors. So we have discussed the passive systems where we can remove harmonics, because mostly we have 5th and 7th harmonics. Third harmonics in loads which are predominantly single phase. Otherwise, it is 5th and 7th harmonic. So we have for third harmonic, we use 14% reactor. We tune the reactor to third frequency, close to third frequency. And for 5th and 7th, we tune it close to 250 hertz. So that is filtration is done. And mostly we find maybe a large percentage of correction can be done with the passive itself. Many places we have found that we can correct the entire harmonic filtration with passive only, but it is not always possible. So we have to use sometimes active filters also. With active filter, we can have a very fine correction as well. Then I'll come to in the next slide. So this is tuned filters we have seen, detuned and tuned, it's same thing. Then third harmonic, we have a special purpose transformer, that is a zigzag transformer. It has limbs in opposite direction where the third harmonic, they get cancelled against each other. Okay. And then the third harmonic is totally removed from the system. Then active filters we have. So before we go to that, I'll just explain how the resonance was being shifted to a safe place with the passive unit. This is a curve where we have only capacitor, plain capacitors. There is no reactor use. So there is a curve between impedance and the harmonic frequencies. If we draw, the system impedance will increase, will attain a maximum value, and then it will start coming down. So the point where the value is maximum, that is the point of resonance. And this point should not be close to any harmonic frequency, because that harmonic will get amplified. So here it is happening at close to 7th frequency. So this is plain capacitor is causing a resonance at 7th frequency. So what we do is we use either a 7% reactor or multiple reactors, maybe 7 for 5th and 7th frequency, or we can use a very fine-tuned reactor. Instead of say 7%, we can use maybe 5.69% or something. So the level of mitigation, harmonic mitigation increases with these things. And in all the cases, the resonance point is shifted to a safe place. Either it is between 3rd and 4th, or it is at 4th and 6th, or some place which is not having a harmonic frequency. So the resonance is avoided with the use of reactors along with the capacitors. So this is how it is explained here. And here we have seen the resonance was taking place at 7th frequency. So there is with a plain capacitor, there is a distortion is there. Voltage distortion is very high. When we are using say 7%, it is reducing. And when we are using a better tuned reactor, it is further reducing. And suppose we have multiple reactors, 5th and 7th, so then it is almost negligible. But we normally don't use multiple reactors because when we are using 7th reactor, there is a chance of harmonic amplification or resonance again at 5th harmonic. So this has to be carefully designed so that we don't cause further resonance. Then only we use multiple reactors. So this is just explanation of the curve only. I can share this thing, PPTs also, and any questions you can ask later on. So this is how the voltage increase I have shown. So then now we come to the active filter. Active filter or STATCOM or SVGs or static var generator, they are all same items, or the grid inverter. This is all same item only. There is no difference between them. Only the application is different. So this can be used for harmonic correction when we generate harmonics 180 degree out of phase with the harmonic frequency. That harmonic is cancelled. So we can cancel any harmonic 5th, 7th, 11th, whatever is there in the system, we can tune. We can configure it to that, and that harmonic can be cancelled out. In passive, what we have seen is we are giving a low impedance path to the harmonic to flow and to get diverted and not to go to the grid. But here what we are doing is we are killing the harmonic. We are just giving an opposite current and we are just neutralizing that. So the working is different in that way. So it can be used for harmonic correction. We can also use it for reactive power support, as in STATCOM. We can generate 50 Hertz current leading or lagging, and we can inject into the system. So it works as a STATCOM. Then suppose there is an unbalance, we can correct that also. We can take care of the voltage dips and sags. And that is what we are thinking, that we can take care of LVRT, HVRT situations, but this has to be designed to that level and it has to remain in the system, then only it can do that job. So this is how we are injecting the current in opposite. You can say there is a harmonic current is there, and this is a load current which has harmonics, and then we are injecting opposite current to that, and then the neutral, the resultant current is normal sinusoidal current. So this is how this is working. Active filter. So we can have a even voltage harmonic correction, the background correction also is possible. Here we have a sensorless control and we can even control the voltage harmonics. But this is not everybody is doing it, only some manufacturers have this facility available. So this is another slide which shows the active when the kVH billing and kWh billing was there, how is the difference? And there is a diagram shown here. If the power factor is maintained close to almost unity all the time in all the 12 months, still the difference is very substantial. And over a period of 1 year, these people had to pay about 11 lakhs extra because of the power factor being not maintained close to unity. This the difference is there. But this is normal. This cannot be always zero difference. But we can always go close to unity. This is another passive filter, which is used directly in series with the what we call VFD. So VFD initially has harmonics from 40 to 60%. If it has a series reactor inside, it will be say 40% or something. If it doesn't have a reactor built in, it will be around 60%. So what we do is we are using this hybrid broadband filter. It has a series filter, it has a shunt filter, both passive. And this takes care of both lower order as well as higher order harmonics. We are able to get up to around 5-6%. And this is, in fact, we are giving it to some companies, OEMs for along with the VFD, they supply this. Then these are APFC components. We have contactors, controllers and all. Now we use thyristors instead of contactors, and thyristors are zero crossover. They don't have any inrush current. The capacitor life is improved. Number of operations could be any amount. Contactors, they will have a slow operation. It will take around 1 minute to respond, but this is almost this can respond within 2 to 3 cycles. So it is a real-time correction we can give it with that. So this is how the equipments look like. These are capacitors which we import from Franco, Germany. Then we have our own Indian capacitors also, MV and HT. This we have our Indian manufacturing as well as we have the imports. And surge protection is there. These are the reactors. These are LV and HV both we are having. So this is contactor switched APFC panel. This is how it looks, thyristor switched panel. And now we have, as I said, medium voltage switched capacitor banks also. We use vacuum contactors up to 33 kV. And we have the APFCs available. Earlier, we did not have APFC beyond LV's applications only. But now it is available, which is being used by all these solar and wind plants also. And this is how a system looks like, outdoor system when we are giving. The shunt reactors. RVT is the protection we have in capacitor banks. Any unbalance can be very dangerous because it can lead to a sort of major accident. And it has to be checked immediately whenever the unbalance occurs. Because what happens is progressively higher and higher voltage keeps getting applied across the capacitor, and there could be an explosion. And as I said, these AP capacitors are there. They are failure mode is short circuit. So they remain in the system, the connection remains, and the voltage increases across the capacitor. In HT, we have this protection. LV, we don't have, we prefer only MPP. Here we don't have so far alternative. APP capacitor is still popular, and MPP, some people have developed, but it is not commercially viable much. This is called SVG or STATCOM, we call it. So this is, we are giving it to industry today. We have given it to renewable plants also for fine correction. Here the power factor, this has become very important because of the kVH billing. We can maintain power factor close to unity with this thing. And rough correction we are doing with either contactor-based automatic systems or thyristor-based system, and very fine correction we do it with this. This is a very recent requirements are coming. Shunt reactors. We have given it to HPCL Mittal Energy. They have a plant where the line is about 11 kilometers long, and when they take a shutdown, the power factor is highly leading. The line length, the line capacitance is about 1200 kVA. And the power factor is going to 0.1, 0.2 leading, and they have a heavy penalty. They used to pay a penalty in maybe crores of rupees because shutdowns are very common. Every month they have 1 or 2 shutdowns sometimes. And during Corona, it was almost a continuous shutdown. So they lost a very heavy amount because of these penalties. So what we have done is we have studied the system, and they were not able to get a solution. They were kVA shunt reactor to overcome the leading power factor, and it was connected in the system at 6.6 kV level. We connected it, and it was able to get the power factor close to unity, even when there is a very low load condition or shutdown condition. Only some maintenance loads are running. And this was done for first, one plant, and then they repeated it for another plant also. So this is again automatic capacitor bank given to Abu Dhabi International Airport. They are HT banks, they are 3.3 kV banks here. This is 33 kV system. 30 MVA given to Sohar Refinery Improvement Project. This is again switched capacitors only. And they are fixed. And now these days we have automation also. And this is one plant was there where they had harmonics. It is a standalone plant, not connected to grid. Suppose when they are connected to grid, it is okay. They have no problems. But when they are running standalone, the system impedance is very high and a very small current harmonic results into a very heavy voltage distortion, about 40%. So, and they were not able to run the plant, and there were failures also, and the meters did not read at all because of this high voltage harmonic. So here passive solutions were given at the furnace secondary level. We could control this voltage harmonic from 14% to around 13%, which is good enough for a small plant, because it is a weak plant, basically, we can call it. Just like we have weak grids, we have weak plants. Yeah. So here we were able to control, and they could run the entire plant with this filtration. Remaining is just we are giving standard solutions, means active as passive combined. Suppose harmonics we are not able to fully control with passive, we give some partly active filters also, and we are able to come near to the IEEE 519 norms. So this is AHF, and then we have the passive systems also. Like this is 725 kVR passive, this is 900 kVR passive, 800 kVR passive is H. But what happens in the industry, we have seen there is a lot of, you can say, marketing gimmick going on. What they do is they say you improve the power factor with passive and use active for the harmonic filtration, two systems. So if we go by that way, the active filters, suppose we have solved the problem with 100 ampere, it will need maybe 1000 amperes. And it's a costly item. So if we customize this passive filter and we remove whatever is possible with passive, this requirements can come down. So that is what we try to do. These are again some similar examples for other plants. This is one solar installation. We have given a solution. It is again 800 kVR shunt reactor and one STATCOM in the substation. They had, it was in MP, they were being charged a very heavy penalty because the power factor was about, again, 0.1, 0.2 leading. And their own consumption was only just 100 kilowatt or something load for the in-house their requirements. And with that, the demand was shooting up to almost 10 times. So they have this is the demand is there, and this is the power factor. And they used to pay 60, 70 lakhs of penalty every month. And here, by putting this, we measured the shunt capacitance requirement, shunt reactor requirement based on the shunt line length, and it was connected on 33 kV side. And fine correction was done on the LT side in the substation. And they could improve the power factor finally up to say 0.9, and this was brought down to normal demand was there about 130 or 120, something like that. It came to that level. So this is what normally I have. So now if there are some discussions, we can have open house, whatever is there, we can discuss.
Sir, first of all, thank you very much for this informative, insightful, mind-blowing, and unique presentation from your side. And I was not the only one who glued to the seat, and even I couldn't blink my eye. It was so wonderful, so insightful, informative. I have some question before I invite question. I have some small question from my end. If you allow me, permit me, I would like to ask. That will
Please.
get benefit.
Yes, sir, please.
My very first question is related to the very simple and relevant part. Everywhere you go, the governments are encouraging solar PV rooftop. And these solar PV rooftop are only supplying the active part. Still, we are getting the reactive part from our distribution transformer. and it has two problems. At my load end, it is making my power factor still more low, and at the distribution end, it is making your heating problem in the core. How to sort out this issue? What is your view on that?
Nani, we have given solutions to these installations also. We have, because we are not dealing with mainly or for the small rooftop available in the housing complexes and all those things. But some industries, suppose there is a 20 kilowatt load was there or 30 kilowatt something, and they had, first of all, this power factor is not because of the solar thing. It is whatever load you are having, your own load, same power factor is reflected there. And the harmonics also, the same harmonics, whatever is there in the load, that is also reflected. The solar inverters, they don't generate any harmonics. And in one place, what we found.
You are right. It is not generating harmonics, but what they are doing, they are supplying the active energy required. They are reducing my active energy requirement. But still, the active power I am getting from my nearby distribution transformer.
Yes. It is not giving you active rate. Just like big solar plant we have today, 100 megawatt or even 50 megawatt and all. Their inverters are also designed to handle only active power. But they are capable of giving you reactive power also. If we want, we can get the reactive power from the inverters, whether it is a small inverter, a rooftop, or it's a big inverter, it can be configured, it can be designed for that, but it is not being done. And the other thing is the harmonics and power factor, they are same as the load, whatever load you are having on the system. We had a problem where they had 70% harmonics, which is unheard of normally. So they had, it's a metal forming industry was there. And there the loads were very highly non-linear. So we had to, and the inverters used to fail very often, and they were not running the plant. Plant was installed and kept under shutdown for a year. Because whenever they wanted to run, the inverters used to fail. They changed the inverter, again, same thing happened. They thought inverter may be inferior. But the problem was their load only, which was non-linear. And we gave a solution at the load level. We corrected the harmonics at the load, and then they could run the plant. Okay. The solutions are similar, just like we have with the industrial installations. It is the same thing here also.
And you mentioned in your presentation that MPP is better than APP. Is true, MPP is better than APP at all. But okay, why don't we take up that matter with the IS code agencies who are making the codes for all these things? Or if one thing is not good for my system and making my system to fail, why these are not being stopped manufacturing? Why we are not taking initiative to stop the manufacturing of APP? We should promote MPP only.
No, it is not like that. We have to give choice to the people, right or wrong. And just like I said about the STATCOM mandate, making it mandatory by the CA, it doesn't work like that. We can't go to component level and standardize the things. We have to leave it to the people. They are experts. They know what they are doing. And they have to decide. In Europe or other countries, you find nobody is using MPP for APP for the low voltage. But India, we still continue to use. It is the people who are not getting, you can say, upgrading their knowledge or upgrading their experience, or they are not concerned. They are having a short-term goal only. APP, they feel, is very heavy duty and it will not fail. And it actually doesn't fail. And that is not a you can say advantage. It is a problem. If it doesn't fail, it will cause an accident. That they are not understanding.
Okay.
It should fail like a fuse. Okay. So, but we can't go to the, you can say, regulations and say that we stop the thing. Let the people take their decision. It should be left to the people.
Last question from my side. You mentioned that STATCOM never helped to take care of the fault current and what to do in such condition and how to make my grid strong. You mentioned that the grid should be strong. What should I do?
That's what grid strong means. We have strong grids. Overseas also, mostly grids are very strong. But in our country, we have some places where the grids are very weak. Our generation, we have added solar, wind, like anything, and they don't add to the grid strength. What adds to the grid strength is conventional plants only, or the solutions like synchronous condensers, or grid forming battery stations with the inverters. So that is how the solution has to be at the base level. if we think that STATCOM, if we put it will solve, it is not going to do that way. That was our point.
Okay.
So grid strengthening is already there. We know how to make the grid strong, and everywhere we have a strong grid. Maybe at some places it is not there. So we have to look at the basic problem.
Okay. Okay. Now I would like to request a participant kindly raise your hand so that I can unmute you one by one and you can ask question.
You unmute everybody, sir. Let everybody participate. There is no problem.
Okay. Kindly raise your hand one by one. That will be better so that the other people can understand your issues and the solutions given by Narang sir. Any question from any participant? Yes, sir. Sunil sir. Welcome to the show. And I was expecting one question from your side. Please unmute and ask your question.
Hello, sir.
Yes, sir.
Am I audible?
Yes,
Yes, sir. Yes.
Very nice presentation you have given to us and very much useful information. I have got some 2-3 doubts that I want to ask you. First thing is that distortion power factor. So while considering the distortion power factor, whether we should consider the total harmonic distortion, whether that is that pertains to current harmonics or voltage or both combined.
No, it is current harmonic only we are calculating.
Okay. My second question is that the resonance condition frequency, generally what is this frequency? Third, fifth or seventh? What should we consider?
No, it is based on the system configuration, your system impedance values. And normally we have found that we have fifth and seventh harmonics. And so long as it is not occurring at that, things are safe. And whenever we find the currents are very heavy and it is due to resonance condition, either it is occurring at fifth frequency or it is occurring at seventh frequency.
While considering or calculating the system impedance, if there is a solar plant connected to the grid, then whether you are considering the impedance of the source impedance of the solar plant or impedance of the grid also.
No, it is the entire grid's entire power system impedance. We have to see that whatever the lines are there, capacitance, the inductance is in the line, the transformers or whatever is there, the entire L and C has to be calculated at the point where we are, you can say, trying to find out the distortion and all. So it should not be matching L and C impedances should not be identical. If they are similar, then this is happening. And once we have made a system and we have put the installations like capacitors and all, so normally system is same, it doesn't change and there is no problem. And only variable is capacitor, which we are adding. And we are having various, you can say, automations also. And when we are adding the capacitors at some point or the other, this may cause resonance condition. Or maybe there are some other changes taking place, some transformer has been changed, or some load configuration has changed. So this is a dynamic condition. Only when there is a change in the system, whatever parameters have changed, that will change the resonance condition or resonance point. Normally, it is because of the capacitors we find. And there is a simple solution also. Suppose we find a resonance is taking place and we have, say, suppose 2 MVR capacitors connected. We can just remove some of the capacitors, the resonance will go away. Or we can add some of the capacitors, again, it will go away. So we know the reason is that it is due to the combination of this L and C. And we have to change, we have to break that combination. That's all.
Earlier you have said that a strong grid. Suppose the power plant is connected to the 132 kV grid through the 33 kV, 132 by 33 kV transformer. Can you say that the power plant is connected to the strong grid?
No, strong means it is not.
From your experience, what do you say?
It is not that just a transformer or something. It is the reactive power support available and it is a consistent backup support with the backup. Like we have a battery backup, you have a synchronous condenser. So we have a idle plant where there is a continuous, you can say, backup available. So that makes the system strong. Solar and wind, they don't make it very strong. unless they have battery backup with them.
Sir, my last question is regarding the rating of the series reactor, tuned series reactor. Generally, what it should be, whatever the kVAR capacity available for the capacitors. So, considering that capacitor kVAR capacity, what should be the rating of the series reactors?
What we do is normally we design by default for the 5th frequency, because if we design for a higher frequency, then what happens is there is a resonance occurring below that. So we design for the lowest, most significant harmonic, which is 5th harmonic. And that is again, suppose 5th harmonic is 250 hertz is the 5th frequency. So we have to design below 5th frequency, and so that it is closer to 250, and it is offering minimum impedance to the that 5th harmonic, and to some extent 7th, 11th also. And this 5th, suppose we say 7%, when we say means 100 kVAR bank should have a 7 kVAR capacitor.
Thank you, sir.
Okay. Now, respected Chandra Prakash, kindly, sir, unmute and ask your question. Welcome to the platform Igniting Power Engineers.
I really thank Narang Sir for a very nice presentation, and I do appreciate the efforts which has gone in making this presentation. As we had interacted in our meeting,
Yes, sir.
that we are actually concerned with how the connectivity of the wind and the solar power plants. 2-3 issues, the issues which are being flagged by the developers to us, that first we are prescribing that that V curve for the inverter, that plus minus 0.95 पे पावर फैक्टर पे आपका हमको कंट्रोल चाहिए होगा, और ये कि एट द टेम्परेचर जो हमारा टेम्परेचर है, normally through the working group report we have said that the ambient temperature plus 1 degree. So many developers are complaining that that condition does not arise, so designing for that aspect of the inverter will be going too far. और दूसरा चीज ये जो विंड के केस में आ रहा है कि हार्मोनिक्स, बिकॉज हमारे सिस्टम ऑपरेटर जो ग्रिड इंडिया है वो कह रहे हैं कि इट शुड बी इन PS CAD, एंड लाइक वर्ल्ड ओवर सिस्टम ऑपरेटर्स दे आस्क फॉर कि इस पर्टिकुलर सॉफ्टवेयर में ही एनालिसिस दीजिए. However, developers are mentioning कि अगर E-Tab में करते हैं तो हमारा हार्मोनिक्स ब्रीच नहीं होता है जो IEEE 519 के अनुसार है, लेकिन अगर हम PS CAD में करते हैं तो इसमें प्रॉब्लम आ रही है. तो ये दो एस्पेक्ट था. अगर नारंग साहब इसमें कुछ elucidated the matter further, तो that will be
just repeat, sir. Pehla, first aspect you told is about the temperature conditions, the derating which happens. Okay. So what is there is it can be always designed when all these active component active systems like AHF or STATCOM or inverter, whatever you have. So they have a derating at when the temperature goes up, there is a derating. So it is failure is another thing. It may not fail, but it will derate at least. So it is very simple. Suppose you have a say 50 megawatt plant or 100 megawatt plant, and you have to consider derating also, and you have to design at that. Only thing is on the capacity will increase. Nothing beyond that. It is so simple as that. So why should they be worried? I don't understand. They can design at 50, so just 1 degree temperature. You are telling them. So their systems may be they may be saying that our inverters are designed for 45 degrees. You are asking them for 51 degrees. So every manufacturer knows what will be the derating at 51 degrees. So he can upgrade the capacity up to that level and he can give it.
No, but अच्छा चलिए ठीक है. And this can be one aspect जिसमें कि cost economics needs to be looked into. Definitely cost will be a part of it.
Yes, sir.
और दूसरा ये जो हो रहा था कि जो हमारा आपने जैसे शुरू में disturbance है happening जिसमें कि वो ट्रिपिंग हो रही है, एंड ये हमारा बनासकांठा जैसे राजस्थान या भुज में renewables at the fag end where the grid inertia is very low. तो आपने उसका जो सॉल्यूशन बताया, एक तो या तो सिंक्रोनस कंडेंसर्स बताया, या दूसरा आपने
Right.
बताया ग्रिड फार्मिंग इन्वर्टर,
Yes,
जिसके
sir.
लिए बेस चाहिए होगा। बट क्या कुछ और भी हम लोग सोच सकते हैं इसके? आपने बोला कि नहीं, सीए का जो ये प्रिस्क्रिप्शन है कि नहीं ये डायनामिक होना चाहिए, तो आपने तो कुछ इसमें बताया भी है, लेकिन इसके अलावा क्या फर्दर, क्योंकि ग्रिड ऑपरेटर का कहना है कि नो दिस 33% इज मैंडेटरली रिक्वायर्ड बाय ऑल द आरई डेवलपर्स। तो ये सारे थोड़ा हम लोग के सीए के में कंसर्न है कि एक तरह तो मतलब बिकॉज एनीवे वी हैव टू हार्मोनाइज द रिक्वायरमेंट ऑफ द जो ग्रिड इंडिया है और ग्रिड का रिक्वायरमेंट है, और दूसरा जो आरई डेवलपर्स है, यू राइटली सेड you already people had put in their money and they are ready to install and inject in the grid, and then the problems arise. So क्या solution further हो सकता है? आपने कुछ बताया कि नहीं आपके solution हो सकते हैं, but ये again this will be a मतलब इसका कोई further और क्या मैथमेटिकल मॉडल या कुछ सॉल्यूशंस आपके पास हो, जो कुछ ऐसा स्टडीज किया हो आपने कि नहीं ठीक है लेट अस टेक कि 100 मेगावाट का सोलर प्लांट है, उसमें हमने ये स्टडी किया और ये पाया। डू यू हैव सच एग्जांपल?
नहीं सर, इसमें वी हैव बीन हैविंग इंस्टॉलेशंस इन इंडस्ट्री सो फार, एंड इन सोलर एंड विंड व्हाट वी हैव डन इज ओनली सो फार automatic capacitor banks are available. And earlier it was definitely a problem because you used to have only fixed banks. Now we have automation up to 33 kV. What we can do to have some better, you can say output, or better, you can say working, is that we can have 2-3 stages. We can have some fixed correction. We can have some automatic correction, and then we can also have some correction at a very fine level, like through a transformer that will be required, through thyristor control systems also we can have. So 2-3, and then finally we can have some correction through a statcom also. So there, suppose you don't put 100% mandatory, then it is simple, because what we can now, if you are having 100% mandatory, we have to 100% import the thing. If you
that's
give
true.
an option,
That is also a concern. That is आपका जो पॉइंट कहना है वो बिल्कुल वैलिड है, क्योंकि अगर हम कोई चीज ऐसा प्रिस्क्रिप्टिव डालेंगे तो वो मोनोलिस्टिक टाइप का चीजें हो जाएंगी। लेकिन इश्यूज क्या है कि अगर कुछ आपके पास इस तरह के स्टडीज होते तो that could have helped us in
today we, for the industry, we are giving hybrid solutions. We have three levels of control. We are doing first control through contactors, second control through thyristors, third control through statcom.
हाँ नारंग साहब, लेकिन यहाँ पे मैं इंटरप्ट करूंगा। जैसे आपने बोला इंडस्ट्री, तो नॉर्मली जो इंडस्ट्री है दे आर इन प्लेस वेयर आपका जो ग्रिड है काफी स्ट्रांग है, दे आर नॉट एट द फ्लैगिंग्स। यू वुड अप्रिशिएट दिस पॉइंट कि आपके इंडस्ट्रीज ऐसे हैं, ऐसे जगहों पे लगे हुए हैं जहाँ पे हमें ग्रिड में इनर्शिया की प्रॉब्लम नहीं है। तो थोड़ा सा अगर कुछ इस तरह का स्टडीज आप लोग फर्दर करते और हम लोगों के साथ शेयर करते हैं।
इसमें भी क्या है, ये सोलर और विंड में भी व्हाट इज हैपनिंग इज steady state condition में your statcom as well as switched banks both are equally good, and in dynamic conditions both are equally bad.
जी
so आपका वो
नहीं, आप बिल्कुल सही कह रहे हैं। अभी एक रिसेंट एग्जांपल आया है जिसमें कि हमने स्टैटकॉम लगाया, जिस पर्पस के लिए लगाया वो पर्पस ही नहीं सॉल्व हुआ। यू आर एब्सोल्युटली राइट इन सेइंग सो। अभी रिसेंट इंसिडेंस हुआ है 8-10 दिन पहले, जिसमें कि सीमेंस का लगा हुआ है, आई एम फॉरगेटिंग द नेम, जहाँ स्टैटकॉम लगाया एंड इट फेल्ड टू ऑपरेट, क्योंकि उनका कहना है कि करंट इंजेक्शन, बिकॉज दे आर ऑल करंट कंट्रोल डिवाइसेस, तो वो सेटिंग ही नहीं चेंज कर सकते। मतलब इन अ सेंस वी कैन से कि हमने जो पूरा इन्वेस्टमेंट किया वो एट द ग्रिड लेवल वो बेकार है। मतलब इट विल बी टू प्रीमैच्योर स्टेटमेंट, but it prima facie means like that only.
So that study which you are asking, because we as all manufacturers, nobody has so far done statcom. Maybe Siemens, you have the example that is very good there. And even in overseas also, people started with this increased inverter capacities as statcoms only basically.
वो आपने ऑस्ट्रेलिया का बोला।
हाँ, then they went back to the normal thing. They say it's no advantage, unnecessary. Why ask the people to spend?
ये कुछ डिटेल्स हम लोगों से शेयर कर सकते हैं। आपने जैसे ऑस्ट्रेलिया का एग्जांपल दिया, या
we are participating in some tenders there, and there is they are accepting anything. Switch banks, they are okay with that. because the grids
Yeah.
are strong. So they have no problem whether it is a switched bank or it is an inverter, both work equally well.
For the RE plants also.
Yes, RE plants only.
तो आप कुछ टेंडर का वो टेक्निकल स्पेसिफिक पार्ट ओनली शेयर
So
कर
I will
सकते हैं जहाँ पे दे आर
share you.
नॉट मैंडेटिंग एनीथिंग
Yes,
स्पेसिफिक.
they are not. I will send you their entire code also. There are, I think, 600-700 pages. I have got the copies. I'll share
जी,
with you.
जी जी. थैंक
So
यू.
there is nothing is mandatory there, sir.
जी 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 जी.
Thank you,
नहीं
sir.
ठीक है, आपसे और डिटेल में बात करेंगे. अच्छा लगा, काफी अच्छा आपने
Thank you.
प्रेजेंटेशन बनाया.
And
थैंक यू.
as
Thank
I
you.
as I mentioned in the beginning, this is our silver jubilee anniversary 25th, and if I stop this presentation without inviting my mentor Apau sir, it will be wrong. Kindly unmute Apau sir and say a few words about this Igniting Power Engineers before we stop.
Good evening, Rajesh. Rajesh ji, once again, I should appreciate your incessant effort in bringing out the continuous webinars as a knowledge sharing session. Today, this webinar is so informative. I could learn several things from Sri Narang. Sir, can you hear me?
Yes, sir. Yes,
Kindly,
we can
kindly.
hear you, but we can't see you, sir.
So it's a very nice informative presentation. Though I am an expert in earthing and protection only, I learned a lot today. But my doubt, when we deal with the regulatory commission on implementation, we had some issues. I want to learn whether that could be resolved, that could be got informed in this session. Actually, the TDD, you have already explained the various formula.
Yes, sir.
PhD and TDD. So TDD is the final factor that accounts for the implementation measures. Here, it again depends on the fault level and the load current. Okay, sir?
Yes, sir.
Load current determines, because the ratio of ISC by IL determines the slab. Again, the actual measurement during that premises, at the premises, makes the difference. So what I want to say here is, in the absence of any specific, or you can call the transparently stating the fault level at a particular location, the people will not be in a position to address the correct harmonics problem. The thing is, the fault level is not known to the consumer. So ISC by IL is not known to the consumer. That alone can, the fundamental principle is to make the grid sturdy. In the sturdy grid, you can pollute more. The weak grid, you can't afford. That's the basis. Here, what people do is, they address the issue when problem arises or when penalty arises. When problem arises, as you said, they can't run the generator with the harmonics. It is because of weak grid. So similarly, why can't we have some stipulations based on the equipment manufacturing stage itself? Suppose, as per, I think there is one IEC TR 6100 series that determines the various emission level. Can the government of India or our India can put a measure to curb any non-standard or highly emitting equipment to gain entry? Because in developed world, there is no such implementation and statutory measures. In India only, we are struggling, it's difficult, and we are having more than 70%, as you said, the harmonic loads. So this is the issue, real concern. Sir, number one, we are not in a position to implement because of the ever-changing grid, what do you call the grid impedance. And another thing, the ineffective or the impossible curtailing of emission limit from the equipments that is supplied to our country. Is there any possibility to impose such things rather than percolating things happen and finally we are coming into for implementation? Is there any possibility?
Yes, sir. You're right, sir. There are two ways of controlling these harmonics. One is that you control at the equipment level, the equipment manufacturing level itself. Earlier, we used to have 6 pulse converters. Now we are having 12 pulse, 24 pulse, and there the harmonics are almost negligible. We don't need any external, you can say, harmonic mitigation system. But still, you will find the maximum use is of only 6 pulse. it is economic, commercial viability is one of the more important factor here. So maybe if you have a 6-pulse converter and you take care of the harmonics separately, that is much cheaper than going for a 24-pulse or 48-pulse and making the system unnecessarily very costly. So it has to be left to the manufacturers, to the users, what they want. We can't, as I said earlier, we should not go to the component level and specify the things how should be done. Let the market decide, let the commercial concerns and the parameters, they will take care of it. Harmonic mitigation is the final. You have to do the harmonic mitigation. How you do is, it is up to you only. What is the best solution case-to-case basis? It can be done like similarly as we said about the reactive power support. You can have inverters of higher capacity or you can put add-on systems. Add-on systems are much cheaper. So let it be decided by the people who are taking the, you can say, who are putting the units. So it should be left to them only. Only the parameters you can decide. I want this much harmonics only. We don't want it to go beyond the IEEE 519 norms. That is, we can only say the final requirement. We can't go to the downwards level and say that you do like this and then achieve it. So that is not workable and that is not proper also.
Yes, I agree, sir. But our people are not so sure to curtail any, because the manufacturer can supply a low level of emission product at Europe and higher level of emission product of his own product in India. How can we address these issues? At least can we, if see whether we are seeing the intricacies or not, at least we can put some level, some emissions, just adopt IEC. Whether we don't know whether they will abide by it or not, but there could be some restriction. There can't be any full-fledged.
You're right, sir. Is what happens is no, people don't take action on their own. People have been running their plants with 40%, 30% harmonics. There have been failures. They just exchange the component, again continue to run, but they don't take any action. They find it much cheaper than taking the action. So the solution is the mandatory requirement here at the final level. Now the IEEE 519, it is made mandatory, and suppose there are penalties now, then they have the payback period in that. If there are no penalties, they don't find it worthwhile to invest at all. So it has to be done by compulsion only. Like power factor, people used to maintain only 0.9 when there was no incentive. When the incentives came, everybody was maintaining unity. So it is commercial considerations are there, and we have to address it from that angle only. The solutions are always available, but we have to find the way. Like in Tamil Nadu, they introduced 15% penalty. And there, as you initially said, how to measure, they were measuring the harmonics TDD close to the full load. When the load is 80% or above, then only they were taking the harmonic levels, and that is close to TDD level.
Yes, I agree. Because we are participating in the particular implementation process. Yes. Finally, because only Maharashtra and Tamil Nadu have come out with the implementation process, but it has started taking place. But the field reality is something others, something else. It is not the actual thing we are.
So these regulatory commissions have to impose the, you can say, these norms, because utilities also may not be very enthusiastic. As I said, they have to pay reverse penalty on voltage harmonics. And that penalty may be larger than the current harmonics they will get from the consumers, some consumer. So they are also not very enthusiastic. It has to be imposed only.
Actually, utilities are getting penalized because of non-implementation.
Yes.
The thing is, the utilities, they are not in a position to declare their ISC. That is the main point. This is all over India. We are not declaring that ISC, because without declaring the fault level, we can't fix the ISC by IL. That is not declared. It is taken as a thumb rule only. That's the problem. Okay.
Sir, thank you very much for sparing your valuable time and giving your suggestions. And thank you, Narang Sir. Thanks again. And thank you all the mentors. I bow my head down and I need your blessings to continue my efforts for more webinars to come. Thank you, everyone. Thanks a lot. Thank you, sir. With that, I close the session.
Thank you, sir. Thank you, everyone.